You tap a button on your phone, and a car shows up. I mean, it feels like magic, right? Almost instantaneous.
Yeah, completely effortless on your end.
Exactly. But in those 2 to 5 seconds between you requesting that ride and a driver actually being assigned to you, there is this massive, high-stakes mathematical war being waged by an algorithm.
It is an invisible war.
Yeah.
And it happens, millions of times a day. So today we're taking a deep dive behind the curtain to look at the exact mathematics dictating that specific moment.
Right.
In the industry, this logistical nightmare is known as earner-offer timing. And our sources today focus really heavily on how rideshare platforms design their dispatch algorithms to handle this.
So to understand just how high the stakes are in those 5 seconds, we really have to look at the absolute worst-case scenario.
Oh, for sure. You need a stress test.
Right. We need an environment where the volume is relentless, the stress is high, and the human beings involved are just at peak impatience. So let's talk about the LAX dilemma.
The Los Angeles International Airport, it is honestly the perfect crucible for this kind of math. So imagine you're a rider, right? You've just landed at LAX. You're standing outside the terminal, you got your luggage, you're super jet-lagged, and you open your app to request a ride.
Instantly, the system checks the queue of available drivers. But the nearest available driver right now is 5 minutes away,
Yeah.
sitting in some far-off staging lot.
Yeah, and the system knows something crucial about LAX. It is a massive, highly volatile hotspot.
Right.
Every single second, new drivers are just pouring into the airport perimeter. I mean, they're finishing drop-offs, they're entering the geofence, constantly refreshing the pool. And this creates an immediate, agonizing trade-off for the algorithm running the show.
Because if the system dispatches your ride immediately to that guy sitting in the staging lot, everybody loses.
Exactly. It's terrible for everyone.
You, the rider, have to stand on this chaotic curb waiting a full 5 minutes, just staring at your phone. And the driver has to make this long, unpaid drive through horrendous airport traffic just to get to you.
Which the industry actually calls a deadhead. It burns gas, it wastes time, and it is deeply unprofitable for the driver.
But if the system decides to hold off, if it waits, say, T seconds, a brand new driver might enter the queue.
Right, someone who happens to be dropping a passenger off right at your specific terminal. They're closer, they're cheaper to dispatch, and the match is just infinitely better.
Okay, you know what this reminds me of? It's like hunting for a parking spot at a crowded grocery store on a Sunday afternoon.
Oh, yeah. The worst.
Right. You pull into the lot, and you immediately see an open spot. But it is at the very, very back of the lot, like near the dumpsters.
Yeah, miles away.
So you have to decide. Do you take that guaranteed spot right away, knowing you have to walk a mile in the rain? Or do you slowly circle the lanes near the front doors, risking that you'll just waste 5 minutes, get totally frustrated, and end up with nothing at all?
That is exactly it. That grocery store parking lot perfectly captures the underlying anxiety here. Because the danger of waiting too long to park is that you just get mad and drive away to a different store entirely.
Yep, I've done that.
Right. And in the rideshare world, the danger is that the rider gets impatient and hits the cancel button. If you cancel, the company suffers a total loss of the trip. Plus, there's structural brand damage. The next time you fly, you might just open a competitor's app instead.
So the app somehow has to manage my grocery store parking lot anxiety. Like it has to know exactly how long I'm willing to circle.
To do that, the platforms use what are called micro-batching windows. So instead of greedily assigning you the very first driver it sees the millisecond you hit request, the system intentionally pauses.
It just waits.
It creates a window, usually like 2 to 5 seconds. And during that tiny window, it scoops up all the incoming rider requests and all the incoming drivers, batches them together, and evaluates the entire board to see if a better global match exists. And to prevent you from abandoning the app, it runs a stop-loss timer. It basically sets a hard mathematical limit on how long it's willing to wait for a better option before it just cuts its losses and assigns you the guy who's 5 minutes away.
Which means if the batching window is too short, the match quality is terrible and the driver deadheads. But if the window is too long, my patience runs out and I just vanish.
Precisely. It's a delicate balance.
But wait, how on earth do you turn human impatience into a math equation? I mean, you can't just plug annoyance into a calculator.
Well, actually, you kind of can, and they do. This whole scenario falls under a formal mathematical discipline. It's an optimal stopping problem, and engineers model it using a framework called a Markov decision process, or an MDP.
A Markov decision process. Okay, we need to break that down. How does a machine process a messy human problem like this?
So think of an MDP as a way for a computer to play a highly complex board game where the rules of the universe are governed by pure probability.
Okay, a board game.
Yeah. To solve the board game, the machine breaks every single moment down into four key components. You have state, action, transition, and reward.
Let me see if I can map this to the board game idea. If I'm playing chess, the state is just the exact position of all the pieces on the board at any given second, right? So for the app, the state would be assessing the current reality.
Precisely. In this case, the machine evaluates a massive matrix of variables to define that current state. Like, what is the distance of the current best offer on the table? How many milliseconds have you, the writer, already been waiting? What is the current density of drivers in the immediate 2-mile radius?
It takes a snapshot of reality.
Exactly, which leads us to the action.
Right, so if the state is the board, the action must be the moves I'm legally allowed to make. And here, the machine really only has two options, doesn't it? It can either dispatch now, or it can wait.
It is a beautifully simple binary choice. Dispatch now or wait. But the complexity really explodes when we get to the third component, which is the transition.
Because if I choose to wait, the board changes. Like, the pieces actually move.
And they move unpredictably. If the machine chooses to wait, it transitions to a new state. This transition involves two competing risks fighting against each other, both modeled by probability.
Okay, what's the first risk?
On one side of the ring, you have new drivers arriving. The system models these arrivals using a mathematical concept called a Poisson distribution.
Wait, why a Poisson distribution specifically?
Mhm.
Why not just, look at the average number of drivers who arrive every minute and divide by 60?
Because human movement isn't a metronome.
Right, it's messy.
Exactly. If drivers arrived exactly every 10 seconds, like clockwork, you wouldn't need complex math. But reality is clumpy. You might get 3 drivers entering the airport in a single second and then nobody for a full minute.
Oh, that makes sense.
So a Poisson distribution is a standard tool in queuing theory, basically because it calculates the probability of random independent events happening over a continuous interval of time. It helps the machine guess the likelihood of a driver magically appearing in the next 3 seconds.
Okay, so it's mathematically predicting the likelihood of a better driver showing up. That's the upside of waiting. What's the downside?
The downside is the second risk in the transition phase, your cancellation. As the wait time increases, the mathematical probability of you hitting cancel also increases.
Wait, let's unpack this. So the machine actually assigns a hard decay rate to my patience. Like, it calculates exactly how fast my tolerance runs out while I'm just staring at that little loading spinner on my screen.
It really does. It builds an exponentially increasing curve based on millions of past rides. The longer you wait, the sharper the spike in the probability that you will abandon the request. It mathematically models human frustration.
That is wild. It's literally using cold, hard calculus to map out my feelings of annoyance.
It has to map your annoyance because your annoyance directly threatens the final component of the MDP board game, the reward.
Ah, the payout.
Right. If the system chooses the dispatch now action, it secures an immediate guaranteed reward, which is the financial value of the trip. If it chooses the wait action, the immediate reward is 0.
And waiting carries that ultimate existential threat. You get annoyed, you cancel, and the potential reward just vanishes forever.
Exactly.
So the machine is basically staring at the board, holding a guaranteed payout in one hand and holding a lottery ticket for a better payout in the other. But the lottery ticket might spontaneously combust if I get too annoyed.
That is a perfect way to put it.
So how does it actually make the choice?
It uses something called the Bellman equation. This is really the heart of the algorithm. The Bellman equation is a recursive formula that calculates the true value of any given state.
Okay, recursive meaning.
Meaning it literally weighs the immediate payout of the current best driver against the expected value of waiting. And expected value here is a very complex calculation. It's the probability that you haven't canceled yet multiplied by the potential value of a newly arriving driver minus the risk of losing everything.
And since it's recursive, it's not just looking one step ahead, right?
Yeah.
It's playing out the whole game.
Yes, exactly. It calculates the value of waiting for 1 second, assuming that in the next second it will also make the optimal choice, and so on. It's this massive cascading tree of probabilities.
Okay, we've built this incredibly complex equation. It's weighing the current offer against the statistical clumpiness of a Poisson distribution, calculating recursive future states, all while racing against the ticking exponential time bomb of my patience.
That's the reality of it.
But you're telling me this algorithm is doing this in 2 to 5 seconds, live. How does any system solve that kind of math in real time without just melting down?
Well, to understand how they solved it practically, we first have to look at how mathematicians solved it theoretically. Historically, this type of optimal stopping problem was explored through a famous thought experiment called the secretary
A
problem.
secretary problem. How does that one go?
So imagine you are an executive hiring a secretary. You have 100 candidates waiting out in the lobby, and you have to interview them one by one. After each interview, you must make an immediate decision. Either hire the person sitting in front of you right now or reject them forever and move to the next candidate. You cannot go back to a rejected candidate later.
Oh man, the FOMO would destroy me. Like if candidate number 3 is great, do I hire them? What if candidate 99 is a total genius?
Right, the uncertainty is killer.
But if I wait for a 99 and they're terrible, I'm stuck. How do you know when to commit?
Well, mathematicians proved there is an analytical rule for this. The mathematically optimal strategy is to automatically reject the first roughly 37% of the candidates.
37%.
Yeah, the exact math is n divided by e, where e is Euler's number. You basically use that first 37% purely for information gathering, just to figure out what the baseline of talent looks like.
Okay, so you're just scouting.
Exactly. Then, the moment you pass that 37% mark, you immediately hire the very first person you interview who is better than anyone you saw in that initial batch.
So there's an actual mathematical cheat code for knowing exactly when to settle.
There is, and it guarantees you roughly a 37% chance of hiring the absolute best candidate in the entire pool, which is remarkably high given the constraints.
That's fascinating.
But while the secretary problem is this elegant theoretical baseline, it's just too rigid for the chaotic reality of an airport rideshare queue. In the real world, the true winner isn't a fixed rule like 37%. It's something called a threshold policy.
A threshold policy, how is that different?
In a threshold policy, the algorithm establishes a specific standard for what constitutes a good enough driver match. But the key difference is that this threshold is not static. As your wait time increases, the threshold monotonically decreases, meaning the curve only goes down.
Oh, okay, wait, I see exactly where this is going. This is online dating.
Oh, absolute.
Or house hunting. Think about it. At the very beginning of your search, when you first download the dating app or start looking for an apartment, your standards are absolutely sky high,
You want the perfect match.
right? All the boxes checked, no compromises.
Yeah.
But as the deadline approaches, or, as the psychological toll of swiping sets in, your threshold for what is good enough starts to drop.
It really does.
By month 3, you're looking at an apartment with no windows and saying, well, the commute isn't bad. The longer you wait, the more you settle.
The dating app is honestly the perfect parallel because it completely mirrors the Bellman equations logic. The system recognizes that the longer it forces you to wait, the higher the exponential risk that you will abandon the app entirely.
So the expected value of waiting plummets.
Exactly. So as the seconds tick by, the algorithm literally lowers its standards. In the first second, it might demand a driver who is 1 minute away. By second 4, it becomes willing to accept a driver who is 5 minutes away just to get you matched before you hit cancel. The computer learns to settle to secure the reward.
That is brilliantly observant of human nature. But we still haven't really solved the speed problem. If the machine is doing this complex, recursive Bellman math and dynamically lowering this threshold for every single person opening the app at LAX simultaneously, wouldn't the server farms just catch fire? LAX has thousands of people doing this all at once.
Oh, if the servers had to calculate the Bellman equation from scratch for every rider on the fly, they absolutely would catch fire. Engineers refer to this as the curse of dimensionality.
The curse of dimensionality.
Huh.
Sounds intense.
It is. Because the state space, the sheer number of possible combinations of time-weighted, drivers available, distances, and cancellation probabilities, it's practically infinite. It is mathematically impossible to compute in real time.
So how do they get around it?
The engineers employ a brilliant workaround. They separate the brain into 2 distinct phases: offline training and online serving.
Offline training. So they're doing all the heavy lifting before I even step off the plane.
Exactly. Offline, using massive server clusters, the system runs deep reinforcement learning models over vast oceans of historical data.
So it's practicing.
Yeah, it plays the MDP board game billions of times in the background. It calculates all those complex Bellman equations, figures out exactly what the dropping threshold curve should look like for LAX at, say, 5 p.m. on a Friday, and bakes all of that learning into a simple cheat sheet.
What kind of cheat sheet?
It creates a massive pre-computed table, so when you are actually in the app, live on the curb, the algorithm isn't doing any calculus at all. It simply executes what computer scientists call an O of 1 lookup.
O of 1, meaning it takes constant time.
Yes. Whether the table has 10 entries or 10 million, it takes the exact same fraction of a millisecond to find the answer. Live in the app, the system just checks the pre-made table.
Oh, wow.
It says, okay, the rider has been waiting 3.2 seconds at LAX Terminal 4. The threshold for a match right now is X. If the current best driver meets X, it dispatches. If not, it waits another fraction of a second and checks the table again.
That is incredibly clever. It outsources all the genius to the offline servers.
Right.
But even with a lookup table, tracking every single millisecond and every single foot of distance a driver moves seems like it would make the table way too big to search instantly.
It would, which is why they use a technique called state coarsening to shrink the cheat sheet down.
State coarsening.
Yeah, instead of tracking continuous granular data, the system lumps the data into coarse buckets. It doesn't track milliseconds, it groups time into discrete 5-second blocks.
Oh, okay.
It doesn't track exact GPS coordinates, it buckets the value of the drivers into maybe 10 categorical tiers. By coarsening the reality, the infinite state space collapses into a very manageable table.
Okay, so they simplify the board game to make it playable.
Yeah.
But let's bring this back to the chaos of the real world for a second.
Sure.
You find a driver who meets the lowered threshold. You offer them the ride. What if the driver just ignores the ping or rejects it? Am I just sitting there waiting while the system sequentially asks one driver after another?
If it did that, your wait time would skyrocket and you'd cancel. This is a very real bottleneck. And it's why the system might utilize something called a fan-out problem.
The fan-out problem.
Right. Instead of offering the ride to one driver, the system might blast your request to multiple eligible drivers at the exact same time. It's a race. The first driver to tap accept gets the fare.
Oh, a race condition. That seems way more efficient for me. Honestly, why not just blast my request to all 50 drivers currently sitting at the airport and see who bites first?
Because if you fan out too wide, you trigger what's called a cancellation cascade.
A cancellation cascade.
Yeah, imagine the system blasts your offer to 20 drivers. Driver A taps accept. But half a second later, driver B tapped accept too. Because driver A won the race, the system now has to artificially revoke the offer from driver B.
Oh, that'd be so annoying for driver B.
It completely ruins their user experience. It flashes on their screen and just disappears. If the algorithm constantly teases drivers with fake rides, they stop trusting the app and jump to a competitor. So the engineers have to manage this fan-out limit with extreme precision. Usually, they cap the simultaneous offers to a strict maximum of 3 drivers.
Wait, we've only been talking about my impatience as the rider. But the driver's a human being too, right? And they have their own breaking points and they're just trying to make a living. Does the algorithm care about them?
It is forced to care. The algorithm operates as a two-sided MDP. It has to fiercely protect the driver's time as well.
Because if it doesn't, they leave.
Exactly. Imagine the worst-case scenario. You wait 4 seconds, the system matches you, the driver accepts and starts driving toward you. But they get stuck in terminal traffic, you get annoyed, and you cancel while they are en route.
Oh, man.
The driver suffers what economists call negative utility. They've driven a deadhead trip, burned costly fuel, lost their place in the airport queue, and received 0 fare. If the mathematical threshold policy allows that to happen too often, the platform literally loses its workforce.
It is a razor-thin balancing act. And this isn't just theoretical math happening in an MIT lab somewhere, is it?
Yeah.
Uber actually rolled out this exact framework globally, right?
They did, across more than 400 cities using deep reinforcement learning to solve optimal starving.
That's huge.
And it's universally applicable. The entire logistics industry relies on it. For example, a private aviation company called Wheels Up uses a remarkably similar expected value model.
For private jets.
Yeah. Instead of rideshare cars, they use it to determine the optimal timing for dispatching flight crews to private jets, factoring in the probability of the crew actually accepting the assignment. The math of timing and human cooperation is universal.
Okay, but I have a major edge case question here.
Hit me.
The entire premise of this offline training relies on historical data. They know LAX because millions of people have used the app at LAX. What happens if a company launches in a brand new city or opens a brand new airport hub. They have literally zero historical data. How does the algorithm know my human impatience decay rate if it has never seen a rider at that airport before? It can't build that offline cheat sheet.
You've just identified the cold start problem. It is one of the most notoriously difficult challenges in all of machine learning. You're right, they don't have the data to build the threshold table. So they have to fake it.
Fake it. How?
Tech companies use pure simulation. They build a virtual matrix-like version of the new airport. They populate it with simulated software agents acting as drivers and rider.
Like little digital people.
Exactly. They program these agents with generic assumptions about human frustration, and they train the initial algorithm in this simulated video game environment.
They literally run a SimCity version of the airport to guess how annoyed I'm going to get.
They really do. They deploy that simulated baseline model to the real world on launch day. It's an educated guess. But then, as real humans start opening the app, and crucially, as real humans start getting impatient and canceling their rides, the system ingests that live data.
Oh, so it learns on the job.
Yes. It fine-tunes the algorithm on the fly, adjusting the mathematical decay curves until it learns the true, unique impatience rate of that specific new airport.
That is absolutely mind-blowing. To step back and just look at the big picture here. Behind every single loading screen, behind that little spinning wheel you stare at on your phone, is an absolute masterclass in optimal stopping.
It really is.
We're talking about Markov decision processes, modeling the board game of reality, Bellman equations recursively calculating the future, and decreasing threshold policies intentionally lowering standards to secure a match.
And all of it operating in a micro-batching window of just a few seconds, looking up values on a pre-computed table to perfectly balance your desire for a better match against the rapidly decaying half-life of your own patience.
So the next time you're standing on a curb staring at your phone and you wait exactly 4 seconds for a ride to be accepted, remember what's happening. You're experiencing the exact calculated millisecond. A machine decided that its mathematical threshold for perfection had dropped just enough to match your predicted level of frustration.
It's a fascinating reflection of our own psychology, really, mirrored back to us in code. These algorithms have mathematically perfected the exact moment to stop waiting and just settle, based entirely on the decay of time and the rising existential risk of walking away empty-handed.
Wow.
And it makes you wonder, if you applied a strict stop-loss timer and a mathematically decaying threshold to your own life, like when you're weighing a major career move or searching for the perfect home, would you be more efficient? Or would you just be less human?
Man, that is a question to keep you up at night. The invisible math war isn't just in our phones, it's practically a philosophy. Thank you so much for taking this deep dive with us and for letting us unpack the hidden calculus of your daily commute. We'll catch you on the next one.